This is AP Calculus Unit 10, Lesson 3. We are on our last lesson for the unit. So 10-3 is right here. And we're back to general fundamental theorem of calculus applications. And yeah, so let's do this. So here's your basic setup. We want to talk about paths of the integral. In terms of the length of the notes, it's about the same as yesterday. And kind of similar to yesterday also, we're basing all of the knowledge today off of previous knowledge and extending it into new types of functions. So I have some weird curve here. It needs to have a mountain here. It has to have a value here in between some interval a and b. And I should say a and b, those are the endpoints. I guess I can label that over here. A, b, those are endpoints. And they usually are. That's common notation in all of calculus. So what type of integral do I have here? We talked about our three types yesterday. You want to refer back to the notes from yesterday or remember?
Isn't there like infinite or definite or something?
Yeah, infinite, definite, or what was the third one?
Accumulation.
Accumulation, yeah. So which one is this?
Accumulation.
Good guess, but no. I'm specifically looking between A and B.
Definite.
Definite or finite, exactly. Yeah. So I'm looking at this definite integral here, and we call this curve. It's not really anything fancy, but we just call it an interval. Interval. And that's just a fancy word for it's like the chunk that you're looking at. So this is the chunk of curve. And I don't know how okay we are with the word curve, but especially when you go into college math, they always talk about curves. You really just think about the curve as the line that is drawn by the function. So curve is really just another word for the function. So it's the chunk of the function, but specifically the line that that function draws through the graph. All right, so when you're on this path, we need to figure out, like on the homework eventually I'm going to be asking for, where is the absolute maximum, where is the absolute minimum of the integral? So let's talk about where I can have possible max and mins of area. So let's just talk about max and mins of a function. Where is the max and minimum of a general function? Not this function in particular, but where do you have maximums, relative maximums, and relative minimums? What's the definition from yesterday?
Prime going from positive to negative.
So that's relative extrema. Rosalie, you're correct. It is a sign change. And where are all the possible sign changes? At CVs, exactly. And what are CVs again? Yep, where what does not exist or is equal to 0? F prime, exactly. So this is just a graph of f of x, I should say. I should go back to blue here. If this is a graph of f of x, we are looking for f prime, as Joy pointed out. So we're looking for, what is it, height, slope, concavity. On this graph of f, if I'm looking for f prime, what am I looking at? Slope. So I'm looking where slope is 0 or does not exist. So there are 2 points where the slope is 0 or does not exist. Go ahead and mark somewhere down here some x coordinates. I'm just doing those randomly. There are 2 of them. Go ahead and mark those x coordinates on your own notes. See if you can get them the same as where my notes are. So the 2 x values I have for my CVs are here and here. I'm going to call this C1 for CV1 and C2. The reason I chose those points is because if I look at that point, I should have this horizontal tangent, and I'll have a horizontal tangent up here. My point is a little bit off, but it's right there. I said was my point of tangency. So that's where, for both of those, we'll say f prime was equal to 0 for both C1 and for C2. And we give those the name CVs. CV stands for what? Critical values. Thank you, Kaylin. Yeah. All right, so there's our good warm-up. We know what's going on here. Let's talk about absolute minima and then absolute maxima. And then after that, we're going to talk about, oops, I grabbed the wrong piece of paper, a table, how to set it up. So there's going to be, I'm going to space out my slides a little bit more than yesterday. So let me make sure that I have enough slides because there. So I don't have to copy paste. All right.
Sorry.
So next up, I want to just talk about absolute minima. When I talk about absolute, you might be able to distinguish this from a relative minima. Do we know the difference between relative, and absolute? I mentioned this in a previous lesson, but I can kind of formally define this right here. Relative versus absolute. What do we think?
It's like absolute is general, like total distance, for example, and relative is like at one point, or like.
Not exactly. So how, maybe a graph, so you don't draw this graph on your page, but if I have, say, a graph that looks like this, I can say I have a relative max here and a relative max here. But one of these is an absolute max.
Because one is like strictly the max, like there's no doubt about it that it's the max.
Yeah, exactly. So that's a good way of thinking about it. So relative, it is a, we'll just say it's extremum locally. It is extremum within this certain, like if I look at this certain interval right here, it is the maximum. But if I take the interval of the entire function, it's no longer the maximum. So the way that I say that is the relative is the extremum locally. Absolute is the extremum for the total function, for entire. Cool, and then I can get rid of these.
So it's like if you're asking for the absolute one, you don't look at all of them, just the biggest one.
Just the biggest, or just the smallest if I'm talking about a minima. So let's make 3 small graphs in our notes. And we are only looking at the first quadrant, so we only need to make them look like this. And I can copy and paste those axes. All right, I'm going to draw 3 different functions here. So the first function that I'm going to draw looks like this. For entire, yeah, bad handwriting, and it's too small. We'll go from A to B, and I'm going to have a dot here, a point here, and a point here. So it's going to go up, down, and up. And the next function is going to start up high, go down low between A and B. And it's going to kind of do the same thing, but reverse, kind of mirrored. I can draw that better. Do your best to try to mirror what's going on. And my third function is also going to go from A to B, and we'll make them go a little bit closer together like this. And we'll have our function swoop above and below those points. So this lowest point is below the point over here, and this highest point is above the point over here. All right, so I want you girls to circle the absolute minima for each of these functions. And I'll give you the answer for the first one. This is the absolute minima for this function. It is the lowest point on the graph. That's another way of thinking about it. And I will label this. This is the absolute, ABS is absolute minimum. I can write my I better, minimum. All right. Hopefully you found the absolute minimum on the second one. It was right here. This is also the absolute minimum. But the absolute minimum for the third graph is going to be different. It's not going to be an endpoint. Where should I circle on my graph?
The bottom of the.
Yeah, bottom of that first trough, first valley. Yes, that is going to be the absolute minimum. Okay, why did I draw this picture? I need to tell you girls that the absolute minimum can occur at it can either occur at an endpoint or a CV is really what I'm trying to say. So it's not enough to just check CVs, you have to check endpoints as well. And this goes along with what we've already learned. When we're drawing our table of where is the absolute maximum or minimum already, we start by already plugging in the beginning point and the end point, and then we fill in between with all the CVs. This is the logical explanation with a visual representation of why we do that. Do we remember? Don't draw this, but if we have our table before and we said, okay, well, if you start at 3 and you end at 9, and then you'll have to find CVs, and it'll be like 2 or 3.97 and then 6.78. You'd have to find your CVs here, but you'd also have to check your endpoints in our tables before.
We
Okay.
always were like, why does it matter? Because we know it's going to be one of the CVs.
So it might be a CV, it might be an endpoint. These three graphs represent the different possibilities: a beginning, an end, or a CV. Perfect. Okay, so, and obviously we can, I think we can use the same graph to condense space, and we can circle, maybe you can, instead of circle, you could box. So I'm going to use a different color, then box the absolute maximum. So I'm changing the title, absolute minima and maxima. Sorry if you can't fit that in there.
I have a question. How many pages of slides do we have left after this one?
I can probably finish, we just need to make a table down here and we'll be done. All right, so box all the absolute maxima. So this is the absolute max. And it's interesting to point out that this point right here is not an absolute maximum. What would we call that point there? I don't want this in our notes, but just for us to know.
Maybe a relative max?
It is a relative max. Yeah, thank you, Rosalie. And what about this point right here? Someone aside from Rosalie. What do we call that point?
Relative min.
Exactly. Perfect. All right. So box all the absolute maxes. So again, just like absolute minimum, absolute maximum also occurs at endpoints, or it can occur at CVs, depending on what type of function they give. All right, so what if they don't give you endpoints? What if it is, as we were talking about in our last slide, if it is not a definite, if it is indefinite, then what do I do? Because that will happen on an AP test. It could happen, I should say.
You just have to find it for what you have.
Yeah, so what points do I need to check then? I can't check endpoints anymore. So I can only check CVs. So that problem is actually easier than if I gave you a function between two numbers. So if they define a certain interval, you have to check the endpoint and starting point. If they don't give you an interval, then you only have to check CVs. All right, our last part of the notes. Go ahead and make ourselves a table. So it's going to be start plus change equals end type of table. I can make that line straighter using my shift key. Make this line longer. All right, so in general, this is what your table is going to look like. Still, you'll have a time, so I'm just going to do t, and then you'll have a start. You're going to add your change, and that will...
Should we leave that much room?
No. I was just using up the full space. The change is going to take about that much room. The start is going to take about that much room. And the end is also going to be pretty short. All right, so obviously, the points that you need to check A and B. And then let's just use our values from our previous graph. We need to check these CVs. Sometimes you'll have two of them. So you can say we need C1 and C2. You need to check whatever CVs you get. And then your start over here, what is the function notation for the start for all four of these values if our function was f? What is the starting value? F of A, there it is, yeah. So you take that starting value for the time and you plug it in to your start. So all these will be f of A, f of A, f of A, all of these are going to be plus, 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 and then the change. So this would technically be, don't write this down. This is going to be the integral between a and a, which gets rid of the entire integral, so we don't need to write an integral there. So that's blank. So there's, you can say nothing there, scribble, and that's just equal to f of a. All right, our next integral.
That's like the integral from like 0 to 0.
Yeah, exactly. Now this one is going to be integral between what and what? A and C1. Getting our review in here, good. And generally speaking, you're going to be doing an f prime of x dx.
Wait, what do you mean generally speaking?
Because we're going to be taking the integral of an f prime for this entire unit. So everything in here is going to be f prime. Also, you need to know that in order to find a value, you should be going backward. So remember, if you have an integral here, we know that we should have integral between a and c2. We know that this thing that I'm going to draw here, this has to be distance because we have a starting distance, and then this is going to be adding some more distance. So you can think of this as kind of like the velocity. You have to integrate velocity to get back to distance. That's why this has to be an f prime of x dx. That's the rationale behind it. And this is also going to be integral between a and b of f prime of x dx. Okay, and then the next conceptual piece, the last conceptual piece for that matter, for this unit is what goes in here. What do I call this? F of c is not really minus f of a because f of a was already included, so this it's just f of c1. And therefore these follow in key. This is f of c2. This is your value at that function, or your distance if you're thinking of it as particle motion. F of b. No, f of a has already been added to this function to give us c1.
Wait, how come you're not doing? Oh, because a is a constant.
So, and this is very related to what we just did yesterday. So take a moment to really think about this. So if I find f of c1, what I did is I mean, the initial condition is bringing back from the last unit, but I'm look at this c1. The c1 gets plugged into the x. It becomes f prime of c1 minus f prime of a, and f prime of a, we don't worry about that because that's the derivative of a constant. And that will give us our f of c1. That's why this thing is equal to this. All right, so go ahead and write our summaries. The main thing to take away is why we need to look for CVs and endpoints when we're looking for absolute max and min. So this is going to be number 1 on the homework, and then I'm also going to do number 3 on the homework after this. All right, so for number 1, we have a graph of the function. This is f. So f right now, this function right here represents a rate. So f is really a rate. Because the reason I know it's a rate is because g is going to take the integral of the rate to get the position. So that's how to think of this problem. Okay, so let's analyze our integral over here. So sometimes they put a number right in front of here where it's a start amount. So the start amount here happens to be 0. They don't have any start amount, so we don't need to worry about that. All right, and then here again we have our f. F again is our rate that we're looking at. This is the graph of f up here. We can label this f if we wanted to. And what's the start time? Somewhere in this integral it tells us the start time. It is not -2. Be careful. In the integral somewhere.
Oh, it's 0 because at -2 the height is 0.
No, so I think you're using this information. We're not using any of that bracketed information. I did hear someone say 1, and that is correct. The start time is 1.
Wait, how did
So the start time is 1 because,
in the integral?
so it's taking the integral of f, which means we start right here for our line, and then we move to however long we go. This is a continuing function. All right. So we know how to analyze, and what are we looking for? We're looking for absolute minimum. All right. So start time is 1, which means if we're looking backwards into time to -2, we're going to have something that looks like this. And this is just a heads up of what's going to happen. You don't need to write this down. We'll eventually have integral from 1 to -2 when we plug in -2, which means we need to flip these two to go from integral between -2 to 1, so it's in the right order, which means we need to make that integral negative. That's how we transform the integral. Okay, so let's go ahead and set up our table.
Should we write that down?
No, I'll do that explicitly, but just be aware that eventually we're going to plug in a -2. What I'm going to do is I'm going to flip the bounds and make it a negative integral. All right, again, I should have just made that line long. All right, so we're plugging in values of x here, so we'll put an x here. And we have no start. So I could write start plus change equals n, but that is kind of useless. I'm going to have to write a bunch of zeros. I'm just going to say change. Start plus change is just change, and that will equal to the end. All right, so what values do we need to plug in is the question. We know we need to plug in -2, and we know we need to plug in 4. So I know I need to plug in -2. I know I need to plug in 4. But how do I find the critical values?
We look at CVs.
Yeah, so where are those CVs going to be? How'd you get 3? Yeah, 3 is correct.
Because that's the graph of f and
So it's height.
Yeah, so I'm going to back up to make sure that we have the full train of thought, but you are correct in how you're thinking about that problem. So again, CVs are where g prime of x is equal to 0. What is g prime of x equal to? G prime of x was, well, g of x was the integral, so g prime of x is now what? F of x. Perfect. You're remembering from our homework yesterday. Which means I'm looking for where f of x is equal to 0, where the height of this graph is 0. And Joy correctly identified that within this interval from 2 to 4, so we're not including this point over here, it's not in the interval that we're looking at. Oh, actually it is. But we're already including -2 as a CV from a start point. So we don't need to worry about that one. It's already included. So 3 is the critical value that we also need to include.
So, because that's where there's a g prime. Okay, then.
That's where g prime is equal to 0. That is where the height of this function is equal to 0. Perfect. All right, so now we need to find the change. So we need to do, again, so this was going to be the integral between 1 and x, 1 and -2 of f of t dt, but I don't like that. I'm going to change this into the negative integral from -2 to 1 of f of t dt. For 3, this is going to be integral between 1 and x, or 1 and 3 of f of t dt. And this is going to be the integral between 1 and 4 of f of t dt. All right, so now we need to find the integral of f of t. Remember, integral of this f of t is just the area. So I need to find the area between -2 and 1. So -2 and 1, this is just a giant triangle. This is 1, 2, 3 by 1, 2, 3, 4. 3 times 4 is 12, divided by 2, 6. So this integral is equal to, shout it out? -6, yeah. If you're wondering why we have this rule, it's because we're counting backwards. So if you really go from 1 to 2, instead of starting at -2 and going to 1, you're counting backwards, which means everything is backwards. This is now a negative. That's the rationale behind this rule, graphically.
So if you just wanted to keep it without doing the negative, and you just thought about it that way, you could do that.
Exactly, yeah. This is just a shortcut for thinking backwards, I guess. Now we're going to think forward for number 3 and 4. So for x equals 3, we're finding an integral between 1 and 3. So we need to find these areas. So I need to split this up. I'm going to split this up into a triangle, another triangle over here, and a square. So that square is going to be 1 times 1, which is just 1. This triangle is 1 by 1, 2, 3. 3 times 1 is 3. Divided by 2 is 1.5. And that triangle should have an area of 0.5. If I add all those up, that should be 3. And to get 4, this is now going to be a negative 0.5. Down here is a negative 0.5. So this one is going to be 2.5. Wait, yeah, 2.5. And remember, what do these values represent? Negative 6 is really the same thing as g of negative 2. That's really what you're representing here. Don't forget what you just found. This 3 is really g of 3. This 2.5 is g of 2.5.
Wait, wouldn't it be
Or sorry,
4?
4. I don't know why I said 2.5. You're right. I got my wires crossed. All right, so to answer our question, the absolute minimum has to be at one of these 3 points. And which one is the smallest? Right there.
Oh, negative 6.
Yeah, there it is.
It's been a rough day. We're like confused why you circled negative 6.
So it didn't ask for the time or the x coordinate of the absolute minimum. It asked for the absolute minimum. So the answer here is the absolute minimum is negative 6. And if you want to be specific, it's at x equals negative 2, but we don't need that. That's our answer. Absolute minimum is negative 6. Cool. So number 2, you have to use circles, but I think we can do that. Let's go to number 3. Number 3 is going to be a little bit different. So this is on the back. All right, so we have a function.
Why is it so?
So it's shown above. At what value does x have an absolute minimum occur? And explain our reasoning. All right. So this one, notice that they don't give you any equation. So this is really just using your heads, using your knowledge about where the minimum can occur.
What's that? Toy Story quote? I don't want to use my head. And they like ram them.
Oh, the dinosaur.
Yeah, Rex, I remember. All right, so, and we're looking for a value of x. That's going to be the answer that we're looking for. We're not looking for what the absolute maximum or minimum is. In fact, it's impossible with the amount of information provided. So, let's think about this problem. I'll give you girls a few minutes to think about this on your own. And I'm going to stop the video also. So we're back. So, we're talking about the function f. We're trying to find the minimum on f. But it gave us a graph of f prime. So, again, what are the two things that we have to check when we're looking for maximum and minimum? Exactly, endpoints and CVs. I don't know why I did CW. That's not the TV programming that I want. Okay, so endpoints. So our options we have to choose from are x is equal to the endpoint, so 0 and 8. So it could be either 0 or 8, or the CVs. Since this is a graph of f prime, CV is defined by, there's no D and E's, where it's equal to 0. It can be at 4 or it can be at 6. We've narrowed it down, so we have a 25% chance of getting it right. It's one of these points. And it's not, it's still better than nothing.
Wait, Mr. Sino.
Yes.
But I thought it was the graph of f prime, so then how is that?
So remember, the absolute minimum always occurs at an endpoint or a CV,
Yeah.
and we define those using f prime.
So then it's a.
Okay, so now think about what's happening here. I'm going to highlight some things. After my function starts, I have all of this positive area, which means I am going with a positive change. So if I have to choose between 0 or 4, which one is going to be smaller, 0 or 4? 0, because we have all this positive change. Oh, look, we have more positive change, so it's not going to be 6. So already we're eliminated some. 6 had positive, 4 had positive. It's between 0 and 8. And what does your gut tell you it's going to be?
8.
Okay, your gut is wrong. Sadly, it's not 8.
You're just good.
Sorry,
Why
gut.
do you let me down? Why do you let me down?
All right, so we're looking for the minimum. We're looking for the minimum. This is positive area, and this is the negative area. this negative area does not outweigh the positive area. The positive area is much bigger than the negative area. So in total, the total change, the total area here should be positive. Which means in total, B should be, or this point at 8, that should have a more area than at 0. So our answer, absolute minimum at x is equal to 0. But we need to explain our reasoning. And here's how we can say that. This is because we somehow need to say that this integral between 0 and 6 is bigger than, or this area between 0 and 6 is bigger than the integral between 6 and 8. Obviously, we don't really, we could explain that the integral, or this area between 0 and 4 is positive and 4 and 6 is positive. I think that's kind of self-explanatory. The main thing to take away is that this area here adds up to more than this area. So we just want to say that the integral between 0 and 6 of our function of f prime of x dx, that thing is much bigger than the integral between 6 and 8 of f prime of x dx. And I guess since, well, to be more exact, we can say the absolute value. Because obviously it's bigger, it's positive.
Isn't it supposed to be
0 and 0? What do you mean?
Oh, wait, never mind.
I'm just trying to say that this area is bigger than this area.
Why does that matter?
So it matters because we knew that we eliminated 4 and 6 because it had positive areas. So you understand that first, right, Carly? Okay, so we're between 0 and 8. If this area, for example, went like this, then this negative area would have been bigger than the positive area. Then the answer would have been 8. We're trying to say, hey, this area here isn't very big. This area over here is way bigger than that negative area. So that's what we're trying to say in our notation. This area between 0 and 6 is much bigger than that area between 6 and 8.
I get that. I just don't get why that's the minimum.
Yeah, that's exactly how I would do it.
Because all of this area represents change. All of that area represents how much you're going up from your start point. So let's say arbitrarily you started at 0. Then we added on this shape and this shape, so we have a bunch of positive area. We have a bunch of positive area, and we're now at 6. And then we can subtract a little bit of that area, and we still have a positive change. So we are still at a positive distance, even though we hit 8. This is the total change between 0 and 8. We still have a positive distance. To get a minimum, we need to have a negative distance, or you start at 0. We never got to a negative distance.
Oh. So like the reasoning is like to show why we didn't choose 8 and why we chose
Is there another
0.
way we could write it? Okay,
Because
can you just draw some scribbles on your graph and be like, see,
You could say in words, you could say that the area between 6 and 8, all in words, is smaller than the area between 0 and 6. But that's exactly what this is saying, because integral means area. I know, that was difficult. And number 4 is very similar to number 3, and number 5 is similar to 1 and 2. So I think we know how to do all of this homework now.
like I get it now that you explain it, but like I feel like I don't know how to do it on my phone.
Yeah, could we? Do you think we could do the other one?
The next one together? Okay. Let me go and screenshot that.
Or can we do number 2 since we have to do circles?
Well, number 2, if you know the area for a circle, which is pi r squared, then you just take half of that to find the area, and you can find the radius.
Can we like try number 4 and then like go over
Yeah,
it?
like
Yes, okay. I'll go ahead and pause the video. Go ahead and work on number 4.
Oh, the video's been
All right, so we had about 3 or 4 minutes to work on this, and we're still a little bit confused. So my hint to everyone was go ahead and treat this as if you were estimating area. So we're going between -7 and 7 in here. That's why I box these off. So I'm just gonna arbitrarily say I'm gonna make that about 5.
You made that 5? I made it 2.
Sorry.
Okay, it doesn't really matter how you estimate it.
didn't like it.
Okay, everyone did 2. I'll do 2. Okay, now we're kind of the same. It doesn't matter how you estimate as long as it corresponds to everything over here. What would we estimate this shape down here? What is that area?
I said
Maybe like
negative
-3.
3.
I like it. That's what I would have put also.
I said
What about this one up here?
I said 5.
5.
oh.
All right, I like it. 5.
That's okay.
What about this one over here?
I said 1.
That's perfect. That's like it's an estimation. That's all I'm looking for. Okay.
I'm so glad that's perfect.
So, use these estimated values. This is really pseudo calculus. Pseudo meaning it's kind of fake. But this will get you the answer. So, let's test what's happening here. We're going to be doing, at a certain time, we're going to do start plus change will give us the end.
For all of them?
For all of them. Yeah, so what different points do we need to plug in for t? Or I guess it's really x because it says x right here. So let me change this to an x to be a little bit more exact. Come on, grab. X. So what values of x should I plug in? Come on, girls.
2, -3, 5,
No.
7.
Wait, you
Negative
said
7.
-5, -1, 5.
Okay, random room. -5, -1, 5, and 7. One of these will be the answer. Okay, so the start, let's just assume that the start was 0, so we don't have to worry about the start. Get rid of the start, because it doesn't give us a start in the problem either. Okay, it's always going to be equal to the change. And by the way, even if the start was 5 or 10, it'll still have the same answer. So what is the change between 0 and 0? So it's nothing. The end is equal to -7. We haven't changed. Okay, at -5, so now I'm right here. How much have we moved?
We moved 2.
Or sorry, it's not at negative. I don't know what I'm saying. It's still at 0. You're right. It is 0.
I was
Okay, now at -5, I have moved 2, so I'm at 2. Okay, now at -1, I'm at -1. Now at 5, at this point, I am at 4. And now at this point,
5.
I am at 5. Which one of these is the biggest? What's up?
You're adding a new area on it.
Yeah, you successfully add. So 2 plus -3 is -1. That's where the -1 came from. And now this -1 plus 5 gives you a 4. And that 4 plus 1 gives you a 5. All right, so the answer is,
7.
there it is, 7. So you have the answer, but we also need to justify our answer. Okay, so I'm going to erase all of this because I want to have room to explain my answer. Oh, come on now. I'm going to grab everything, but not that. Okay, so here's your answer. So it has absolute max at x is equal to 7. That's the first half. Here's the rationale. We somehow need to say that these areas,
Well, how I said it was the integral of -7 to 7 absolute value f prime of x dx is greater than integral of -7 to 5 f prime of x dx. But I don't know.
so we basically need to say that this one is smallest, then this one is the next biggest, then this one is the next biggest, then this one is the next biggest. But we can say that all at the same time. I can do this really quick. So that's what I'm about to say here. So the way that I say that is the integral between 5 and 7, absolute value, f prime of x dx. So that this thing that I just wrote right here, and absolute value here, this whole thing is telling me the area of 1. Do we understand the correlation there?
Yeah.
So that is smallest. The next biggest is the integral between -7 and -5, absolute value of f prime of x dx. Okay, keep forgetting the absolute value, is the next biggest. Next biggest is the integral between -5 and -1 of f prime of x dx. And then finally, the largest one is the integral between -1 and 5, absolute value f prime of x and absolute value dx. That's your rationale. You basically said what the sizes are And that's really all you need to say for your rationale, for your pieces.
So basically,